let's talk about the error terms that we get from Taylor series expansions, because we have several formulae for approximating the derivative at some point xi. So typically when we're interested in this derivative, we look at equally spaced points around xi. So you might have xi minus 1 here, xi plus 1 here, and you might have more points, but we're mainly concerned with kind of forward differences, backwards differences, and central differences. So the Taylor series expansion works fine in the case where these points are equally spaced, and we're going to consider a 2-point forward difference formula for the first derivative. So we're interested in a function f evaluated at a point xi plus 1 based on the knowledge of xi. So we can use the Taylor series and we can describe it as f of xi plus the first derivative of xi times h plus the second derivative of xi divided by 2 factorial times h squared, and so on. You can pretty much guess what the terms are, or not so much guess as you should be able to tell what they are from the Taylor series. So in this case, I'm using h, which is simply the increment, the distance between the points. So that would be essentially xi plus 1 minus xi. Okay, so we have this formula, and what we can also do, the way that we can rewrite this formula is by using the remainders of the Taylor series. So if we were to rewrite this in terms of the remainder of the Taylor series, kind of ignoring the higher order terms and just leaving a remainder in place, we'll get something like the following. So we'll get f of xi plus 1 being equal to f of xi plus the first derivative at xi times h plus the second derivative at some value xi divided by 2 factorial h squared. Okay, and what we're interested in, at the moment at least, is the first derivative. So we're essentially interested in this part. So we can rewrite this entire thing in terms of the first derivative. We can say that the first derivative at a point xi is actually the function at xi plus 1 minus the function at xi divided by h, and then minus this term, so minus the second derivative at xi divided by 2 factorial h. And notice it's h, not h squared, because we lost one of the h's as we were dividing. Okay, so what this tells us is that we now have an approximation for the first derivative, and this thing on the right hand side happens to be the error term. So this is essentially the truncation error or the discretization error. Let's just call it DE for short, discretization error. So this is kind of the extra part that we would actually be ignoring typically if we were discarding the higher order terms. So essentially what we can say is that this discretization error is on the order of h, because that's the multiplier here. H is the multiplier to this entire thing, and it basically tells us that the smaller the h value, obviously the smaller the overall error is. So this is what it looks like for a forward difference. We can do a similar calculation for the backward difference, and we'll still come up with roughly the same result. In fact, the only real difference is that you would have something like the following. So you would have the first derivative at xi minus 1, xi minus 1 being defined as f of xi minus the first derivative of xi h plus the second derivative, once again at xi, divided by 2 factorial h squared, and once again you go ahead and you solve for the first derivative, and in this case the discretization error is once again on the order of h. So there is a question is whether we can actually improve upon this. So to improve upon this, we'll call upon the central difference, because that's something that's a bit more exciting. So essentially, let's rewrite, once again, let's rewrite the final differences, but have a few more terms, and we're also going to have different psi values for the kind of things that we're going to be looking at. So let's do this. So once again, just a reminder of what the formula are. So for the difference, we have f of xi plus 1 being equal to f of xi plus first derivative at xi, times h plus the second derivative at xi divided by 2 factorial, sorry, this should be a 2 factorial h squared plus, let's have some remainder here. So the third derivative of some value xi1, not very good at drawing these, so this is going to be xi with index 1 divided by 3 factorial multiplied by h cubed. So the idea here is that xi1, which I'll try drawing as neatly as I can, is somewhere between xi and xi plus 1. Okay, and now we're going to have the other side, sort of the backward difference. So essentially we'll have xi minus 1 being defined as f of xi minus the first derivative at xi times h plus this term, then minus this term. The only difference is that when we talk about the kind of final term, the one where the remainder is, we're going to have a different xi value. So maybe we'll have xi2, so xi with index 2, and if xi with index 1 is between xi and xi plus 1, then similarly xi with index 2 is something that's going to be between xi minus 1 and xi. That's the only difference, but apart from that, it's really all the same. So we're going to have h cubed here. Okay, so we have two representations, and for the central difference, what we essentially get is we can actually kind of integrate both of them together. So we can take both of them together, and we'll come up with something like the following. So if you think of, because what we're really interested in is obviously the first derivative, once again, this part, but we cannot just add these two formulas together, because then the plus and the minus will kind of consume each other, and that's not going to be a very nice thing. So essentially we want to perform a subtraction. So let's try doing a subtraction instead. So we're going to subtract this from this, kind of like this, and we're going to have f of xi plus 1 minus f of xi minus 1. Sorry, that minus 1 is actually an index, so it should be a bit lower, xi minus 1 here. And that's going to be basically f of xi minus f of xi. Those disappear. And then the first derivative minus minus gives us plus, so that becomes a 2 first derivatives at xi h. And then we add up this term minus this term. So essentially we have the third derivative at xi1 h cubed over 3 factorial, and then another plus, because this minus and this minus gives a plus, so another minus for the third derivative of psi 2 divided by 3 factorial h cubed. Okay, so now we've done it in such a way that we can in fact go ahead and extract the first derivative, because that's what we're interested in right now. So the first derivative at a point xi is going to be defined as f of xi plus 1 minus f of xi minus 1, like so, divided by 2h, plus these terms. Now remember, we're to get rid of this h, we're dividing by h, so we're going to have h squared here and h squared here. So once again, we can just say that this is h squared. So what we essentially come up with is the fact that for the central difference gives an approximation which is more accurate, because the error term, the discretization error, is actually of a higher order, and that's always a good thing. Now we can just briefly look at the second derivative. So I'm just going to write out the formulas for the second derivative. So f of xi plus 1, we'll do the forward first of all. So that's f of xi plus the first derivative of xi times h plus the second derivative of xi divided by 2 factorial h squared plus the third derivative. We'll have the third derivative of xi divided by 3 factorial h cubed plus the fourth derivative f4 of, once again, we're going to have xi1 divided by 4 factorial of h to the 4, and we'll have a similar formula for xi minus 1. So it's just that the sign, some of the signs here will be negative, so there's going to be a minus here, and there's going to be, well, that's actually not correct. No, there's going to be a minus at this location. There's going to be a minus at this location, I believe. So apart from that, it's going to be almost identical, except that here on the final kind of term, we'll have f4 of xi2 divided by 4 factorial h to the 4. But apart from that, it's all more or less equivalent. Now, what we can do in this case, because we're not interested in the first derivative, we're actually interested in the second derivative, which is this part. What we can do is we can actually add them up. And if we were to add them up, we'll get something like the following. So we'll have f of xi plus 1 plus f of xi minus 1, and that's going to be equal to, so f of xi and f of xi, that's 2f of xi. The pluses and the minuses kind of cancel themselves, but we do get the second derivative. So we get two second derivatives of xi divided by 2 factorial times h squared, and then we have these two terms. So these two terms, they just, they go as they are, so we add them up, and that's where they will be. So once again, if you were to solve for the second derivative, so for this part, because that's what we're interested in, you'll get something like the following. So you have the second derivative at a point xi, which is equal to f of xi minus 1 minus 2 f of xi plus f of xi plus 1, all divided by h squared plus, and this is the important part, order of h squared. So once again, we're getting the error term on the order of h squared, just to explain how this came to be. These are h to the 4 here. However, to get rid of this h squared here, we essentially divide everything by it, and that explains the h squared here. The fact that the second derivative has been extracted without the h squared. So on the right, we have h to the 4, both divided by h squared, and this is why we get this kind of error term. So this basically once again shows that the central differences for the second derivative are pretty good, because they give us an O of h squared error term.